Good morning, everyone. Happy first day. Today we're glad to have Zach Weiner visiting us from University of Washington. So Zach obtained his PhD degree in 2021 at the University of Illinois at Urbana-Champaign with Peter Adsett. And after that, he was a postdoc. Since then, he has been a postdoc at the Washington University at Seattle. So Zach worked on a broad range of topics covering particle physics beyond the standard model, gravitational wave, and various topics in cosmology, including the early universe and the Hubble tension. And today he's going to enlighten us on the cosmology of electron scalars. So Zach, please take it away.
Thank you, Misha. It's great to be here. Today I'm going to be talking about work that I've been doing with Masha Bari-Akhtar, who's a faculty in the particle theory group at UW, and also Olivier Simon, who's a recent PhD from Stanford and will actually be your neighbor this fall. He's going to be joining PCTS, so you should definitely interact with him because he's fabulous. Okay, so Cosmology of Electron Scalars. So, it's not controversial to say we've certainly learned a lot from cosmology, established our Big Bang paradigm for standard model physics, starting off in some hot plasma in the early universe. As far as standard model physics goes, we've also learned quite a bit about neutrinos, that their abundance is consistent with their decoupling with the weak interactions, and you can also place constraints on their mass. But also, of course, there's a whole dark side that's been revealed by our cosmological observations. There's dark matter and dark energy, and also just the surprising simplicity of the initial conditions, which calls for new beyond standard model physics that we, as of yet, don't really know how to connect to the standard model physics that we know and love. And so in that sense, this dark sector raises more questions than it does provide answers. We really have no clue what the fundamental nature of any of these constituents are, whether it's dark matter or dark energy, or the specific details of a possible inflationary mechanism. There are also still open questions that we might hope to address with cosmology regarding neutrinos. And of course, there's always the possibility that there's new BSM, beyond standard model physics, that could be having some impact on the CMB, for instance, that we have yet to uncover. Moreover, there's in some sense challenges to our notion of cosmological concordance. I'm sure everyone's familiar with these crazy plots, but broadly it seems like there are ways in which our model of early universe physics gives inference of our parameters of the Hubble constant and parameterizations of the amplitude of matter fluctuations that seem to be in tension with late universe probes. And so some might argue that this is our first signature of beyond the land of CDM nature of the dark sector. This is compelling in one sense because, of course, as we get more and more data, an improved understanding of cosmology, we are hoping to uncover more details about the nature of the dark sector. So people have introduced a whole zoo of possible modifications to the dark matter and dark energy and whatnot to maybe fix up some of these so-called tensions, including even introducing yet another dark component. But the one problem with these sorts of ideas is that if you're going to invoke them for their own sake, usually they don't lead to any non-cosmological probes that would give us another way to get a handle on such physics. And so from that perspective, if you can come up with ideas that will affect the standard model, well, then we have a bunch more opportunities, whether it be in astrophysics or in laboratory experiments. And so from a falsification perspective, models with new standard model phenomenology are more compelling by this argument. Moreover, even if this tension were to go away today, we're still saying something meaningful about possible extensions to the standard model. And using the data that we get from cosmology to place constraints on such scenarios is certainly a world we never in its own right. But don't take it from me. Listen to Master Yoda, who always tells us to resist the temptations of the dark side. Little did Luke realize that by the light side of the force, Yoda meant for him to study electromagnetism. So that's what we're going to do. Okay, so just to get situated, think about what sorts of new physics we might need or might be talking about. Just to do a lightning review right now of how the CMB measures H naught. In the early universe, sound waves in the photon baryon plasma propagate up until the point of recombination, where the photons decouple. And at this point, those sound waves have traveled some characteristic distance, r sub s, what I will refer to as the sound horizon. And at that point, the photons free stream for the rest of the history of the universe to us today, some distance d sub n. I can rewrite this transverse distance to recombination in a suggestive way, where I've factored out the overall scale, in some sense, the units of this quantity, which is something that needs calibration, and then an integral over, the expansion history, which is really only sensitive to the shape of the expansion history. And that's something that's well measured by our uncalibrated distance measurements. Okay, so if I want to make H naught bigger or smaller, then I need to make the sound horizon smaller or bigger. Okay, now what sort of models can I imagine that might affect the size of the sound horizon? Well, if I rewrite this expression for what the sound horizon is in terms of temperature as the independent variable, then it becomes a bit easier to talk about. I basically just have an integral over the inverse co-moving size of the universe, weighted by the sound speed of these pressure fluctuations. And so the name of the game, I have two choices really. I can increase the expansion rate at any given temperature. This is like this class of solutions is like adding extra radiation and effective solutions or early dark energy. Or I can do something to make recombination trigger at a higher temperature and so an earlier time. And really it's kind of clear to see in this way that I have one option, which is by and large going to ask me to add new contributions of energy in the dark sector. Or in new degrees of freedom, and another option which actually will require me to modify standard model physics in some way. There's also there's the sound speed, but it's kind of hard to imagine changing the evolution of that without ruining the specific structure of the CMB, so we'll just disregard that. Okay, so if I actually want to change the temperature at recombination happens, and so therefore the redshift at which it happens. Note that the temperature of recombination is essentially given by the ionization energy of hydrogen, and that's proportional to the electron mass. If the electron is heavier, it's harder to kick out. And so if indeed the electron is heavier in the early universe, then as I'll explain in more detail later, that makes by making recombination happen earlier, that makes the sound horizon smaller. And so this was proposed a few years ago. The scenario is nice because it's simple phenomenologically, as I'll explain in a little bit. It gives rise to there's basically a perfect degeneracy in the primary CMB in this extended parameter space. However, to get low redshift distance measurements right, you need to, or at least as this original paper proposed, invoke curvature, which is never very appealing. And yet, in a sort of H naught Olympics, as they called it, fair comparison among proposals, in some quantification, this has been claimed to be the best candidate to resolve the Hubble tension, if that's what you're taking as your motivation. Okay, but this paper was like wholly sort of phenomenological notion of this early recombination model, this varying electron mass scenario. So my goal, yes.
Sorry. So the statement is that in order for the electron to become lighter with time, that's a statement about curvature, or is this?
Okay, there's a few more steps. It's not connected to the electron mass itself. It's the way in which you have to adjust the other lambda CDM parameters mess up the shape of the late universe expansion history in such a way that you don't really recover the trajectory of these distance measurements with redshift. Thanks. Okay, so my goal for the remaining time is to just explore the space of actual theories, particle models that would give rise to a varying electron mass. In particular, I'd like to address the questions of, what do we learn from complementary probes, since we actually have those? What are the actual concrete theories that we can imagine? Once you pick a particular theory, is there going to be additional phenomenology that we have to take into account for cosmology? And then finally, I'll present the results of parameter inference on some concrete scenarios. Okay, so I'll start with various probes and then lead into specific models. So I'm going to start with some additional model independent probes that are really just telling you something about the electron mass itself without reference to a model. The first and the earliest one that we have being BBN. So with a different electron mass, you're messing with the rates of neutron to proton reactions during the epoch of weak coupling, and moreover and more importantly, affecting the rate of neutron decay afterward. It's just simple to understand. A heavier electron is harder to decay into. You get less phase space. And it turns out you can do some semi-analytic calculations to derive, how the helium abundance responds to shifts in the electron mass. Long story short, there's a bunch of equations and what symbols on here, but if you take the experimental measurements of the helium abundance along with its error bars, and compare that to the theory prediction, which has, for all intents and purposes, negligible error bars here. And then if I translate the uncertainty in the measurements into an uncertainty purely on the electron mass, as opposed to anything else, I get some bounds on the fractional shift in the electron mass as I'm comparing from the time of BBN to today.
Let me ask, but this shift, you assume that the same shift happens at BBN and at the CMB epoch? Can I engineer a situation where at BBN there is no? Is it possible? Or?
That is what I will focus on. There are ways, yes, there are. I mean, maybe you can imagine such a thing, and indeed there are some effects that would necessarily lead to those values being different. But our goal, for sort of the sake of simplicity and predictability, is to avoid those scenarios. I'll talk about that in a few slides.
Yeah, these constraints will be really kind of intentional with what you need for H0, right? And that's why it's going to be basically this motivation for the models.
Indeed, yes. I mean, if we had to double the electron mass to get any change in H0, then I wouldn't be talking about this. So precisely for this reason.
What's the effect on second?
I will get to that in the very end, but it's a good question. Anything else? Okay. Yeah, so I've got these bounds on how much the electron mass can shift relative to its known value. If you're puzzled by whether asymmetric, that's just because the theory prediction is slightly offset from the experimental measurement. That's all that is. So all I'm really allowed to talk about at the end of the day is mass shifts of order a few percent on either side. Another probe from the relatively early universe comes from quasar absorption lines. So the story here is that you've got some bright quasar, and along the line of sight to us are some molecular clouds. And if one makes measurements of the absorption lines due to various atomic transitions or molecular transitions, and compare those measurements to the known values that you can get in the lab, You can place constraints on variations in the fundamental constants. This has actually been done for decades. Basically, if you just collect a bunch of these constraints, what we're really talking about is part per million level bounds at redshifts of 1 to 5 or so. So that's a pretty striking bound. I know that not too long after a combination, the electron mass can't have shifted by more than a few parts per million. That's an important thing to take into account. Okay, so if we take both of these things in conjunction, I basically have the picture is that I've got some relatively speaking broad limit at BBN, so at very high redshifts. Then eventually recombination happens, and later on I've got these quasar measurements which are telling me so this is a symmetric log scale. Those error bars, while they look large in the plot, are actually quite small. So I have to basically, the simplest picture that Giovanni was asking about is just to have some constant shift all the way up until recombination, and then afterward have this mass shift, redshift away. Now, this notion of something that remains at a constant value and then redshifts at some point is exactly what a scalar field does. So let's think about scalar fields. Indeed, if we look to the standard model for motivation, the mass for all of our particles comes from the Higgs, which is a scalar. Let's forget about the details of electroweak symmetry breaking and whatnot, and just recall that the electron mass just comes from the fact that this scalar field has some vacuum expectation value, some homogeneous value across space and time. Also, for anyone who's not particularly happy to or fluent in speaking particle physics, don't worry too much about the Lagrangians that I'll have in the next several slides. It's just big ideas. So bear with me. Okay, so inspired by the Higgs, let's just postulate another scalar with a so-called Yukawa coupling. This is this orange, these orange characters. This is just a sort of standard way to parameterize these couplings, and I basically just multiply the standard mass term for the electron by some scalar field, which can then modulate its mass. And so the mass shift is basically given by this dimensionless coefficient DME times the value of the field in appropriate units. Okay, so how does that work? Well, let's think about how scalar fields evolve in the early universe. The Klein-Gordon equation basically tells us that at early times, when the Hubble friction that the scalar field feels is much stronger than the force of its potential, that the field will remain constant. That's what we want. And then at some point it starts to roll, and when it's rolling, its value redshifts like 8 to the -3/2. And sadly, that's not enough redshifting to really evade these low redshift constraints. So this model, the simplest thing that we could write down, is already kind of out of the question for us. Moreover, this particular coupling has a whole host of other probes. If this plot is intimidating, it should be. But the only thing that really matters for us is that if I consult this plot, so on the bottom axis, I've got scale factor. This is just the scale factor, or roughly inverse redshift. And then I've got Hubble on top and the units of EV, which is how we talk about masses. And so things after recombination, to start oscillating after recombination, I need to have a mass of order 10 to the -29 EV. Okay, now I'm going to go back to this scary plot. And I basically need to live over here. And it turns out, long story short, that I would need to live up here with some order 1 coupling coefficients. And those are already ruled out, quite stringently by, at least at the level that we care to talk about, by various probes. Okay, so let's move on from this case. What about an axion? Everyone likes axions. what makes an axion or an axion-like particle an axion is that it's shift symmetric, namely the forms of its interactions are proportional to the derivative of the field, not the field itself. We usually like this because it places a strong restriction on the types of couplings that I can write down, which makes the theory simpler to talk about. Of course, on the other hand, it also restricts the various avenues that you have to get phenomenology. But the other nice feature of this shift symmetry is that it protects the lightness of the particle if I want it to be light. Namely, it's in a field theory sense, it is natural for such a particle to have a very light mass. But sadly, in this case, the electron mass shift would be proportional to the field's velocity, not its value, and its velocity is not constant at early times. So this doesn't really fit in with the picture that we're trying to work out. And while we're talking about axions, I'll just take the opportunity to say that I'm sure you've seen numerous talks on axions in cosmology, and I know some of you have even worked on this topic. And I'll just note that as far as gravitational interactions go, there's no difference between scalars and axions. Axions are just a type of scalar, usually differentiated by the types of interactions that they have, and also on occasion the type of potentials they have. So the scalar field potential may be slightly different, but when we're talking about cosmological effects, usually there's no difference. That will be relevant later. Okay. All right. So the two things that I might want first are not really available to me. So what's left is I'm just going to name these, but the details at this point don't particularly matter. There's a pseudo-scalar coupling and there's a quadratic coupling. The only thing that I really want you to remember about physics here is just that the mass shift is now of the same form for both of these, and it's some combination of these dimensionless coupling coefficients times the field value squared in appropriate units. Okay, and so this fact that my mass shift evolves with the field, like the field value squared, is great because now, when I return to this plot, after the field starts oscillating, the shift in the electron mass is going to drop like 8 cubed. And that is fast enough to fit in enough redshifting between recombination and the times when quasar light is passing through molecular clouds.
Yeah, so maybe a technical question. So if maybe how can I understand that in the coupling that the first one that you wrote, the one pseudo-scalar, the shift is proportional to the field?
Yeah, that takes a bit of work.
Okay.
It takes a bit of just gamma matrix muscling, which is the latter, the quadratic one is actually multiplying the standard mass term, and then there's gamma matrices to be miserable about, but yeah. Okay. All right, so now, I've got some models that I can work with. Now that I've specified some specific scenarios, is there anything else that we can say? First of all, we're using the scalar field to shift the electron mass, but it'd only be fair if the electrons also modified the scalar's mass, and indeed this can happen. In the early universe, there's a bath, a plasma of electrons and positrons, and via thermal effects, these can source a effective mass for the scalar field, so temperature-dependent mass. Fortunately, this thermal mass will be exponentially suppressed after E plus E minus annihilation. And so even if the field were to begin to oscillate, it would then refreeze. And recall that E plus electron positron annihilation occurs, factor redshift of 1,000 or something earlier than recombination. But this is a bit of a undesirable feature, as I was mentioning earlier, because ideally would have a bit of a simple correspondence between the field, the homogeneous field's initial condition, and what its value is at recombination. And because the field is oscillating and then it refreezes at some point, random point in its oscillations, it can flip sign or whatnot. So just to avoid all this complication and just have a common electron mass shift at BBN and at recombination, I'm just gonna say couplings have to stay smaller than a few. That turns out to be, as you can see from comparing these various purple and green lines, that's roughly enough to make it so that the field doesn't start oscillating. Okay, another thing that we get is the fact that the scalar field will mediate a new force between electrons, and such a force would appear to violate the equivalence principle, or rather the universality of free fall. There are experiments that measure this with like shocking precision. There's the microscope experiment, which is a satellite on a satellite. And then, just across campus for me at University of Washington is the ETWASH group, which is like the world premier lab for making these measurements. They make these torsion balances where you're basically comparing the gravitational and inertial mass of materials with different compositions, and you can translate their bounds on, details don't matter, but you can translate their bounds on this free fall universality violation into constraints on the model. These constraints aren't really direct constraints on what the electron mass is, but they turn out to, the leading order effect turns out to have the same parametric dependence. So we can talk about it as an electron mass shift bound. And just for simplicity, that's how I'll talk about it. And similar to the quasar absorption lines, this is again a part per million constraint. And I'll also just mention that the pseudoscalar coupling has not yet been considered in the literature for these particular bounds. Okay, so let's put it all together. The parameter space I have, so what I want to think about is what is the mass of my scalar field, and therefore equivalently at what redshift does it start to oscillate? And what is the, how much bigger or smaller is the electron's mass in the early universe, compared to today? And in this parameter space, I have bounds that are mass independent coming from BBN. And I have the bound that I don't want the field to start oscillating until after recombination. That translates to masses having to be lighter than 10 to the minus 28 eV. And then in this gray shading, I basically am indicating what the would-be mass shift in the electron today is. And from the universality free fall and the quasar absorption lines, translated accordingly, I get constraints that effectively look like that gray area. And so the parameter space in which I'm allowed to live is the white. So this is actually not a very broad parameter space at this point, which is sort of exactly what we were hoping to learn by this exercise of trying to put concrete models to this phenomenological scenario in which the electron mass is different in the early universe, which is sort of, I guess, good from a predictability standpoint. And so now that we have a sense of what we're allowed to do, we can run with it. There is, however, one more thing I want to note before proceeding to talk about cosmology again, which is the following. So, like I said earlier, the mass shift is basically just given by a dimensionless coupling coefficient times the scalar field's value squared. And just the standard parameterization is to have the field value be in units of the Planck mass. So inverse root G. And for that reason, I can rewrite the mass shift in terms of the scalar field's energy density, which is roughly given by its mass squared times its field value squared. Now, when I remember that the field begins oscillating roughly when H is equal to its mass, what this basically means is that the early universe mass shift for the electron is proportional to this dimensionless coupling times the fractional contribution that the scalar field makes to the total energy density in the universe. Now, when I combine that with the arguments that it's best to avoid having a large thermal mass in the early universe. And therefore, I want this coupling coefficient to be smaller than a few. What this essentially means is that I can't just, take any energy density in the scalar field and use a really big coupling coefficient to get whatever electron mass shift I want. They're basically tied to be roughly the same. I think even like the numerical coefficient is like 1.5 or something. So this is, bearing in mind further that the field starts oscillating in the matter era, and scalar fields and with a massive potential also redshift like matter. This means that for the entirety of the rest of the universe, so after the field begins oscillating and acting like matter, I have a new contribution to the matter density that is of order however much I have shifted the electron mass. So if I shift the electron mass, if I want an electron mass shift of a few percent, then I necessarily have a contribution to the matter density that's a few percent extra on top of the cold dark matter. Okay, and this is going to be, this is the sort of novel phenomenology for cosmology that I was hinting at earlier. Okay, now I'm going to move on to the actual cosmological signatures. I'm going to just start with vanilla early recombination, so just ignoring the details of the underlying theory and talking about shifts in the electron mass. So if I fix all of the lambda CDM parameters to the best fit from Planck, and then I just vary the electron mass, I guess the 20% in either direction, this is the result, and you get a bunch of pretty curves. But there's it seems like there's some sort of like self-similarity here. So maybe we can just adjust the lambda CDM parameters in some proportion to the electron mass to offset this change that's been that we see here. So the first thing that we need to do is to get the location of these acoustic peaks right. That is in some sense, the best measured thing in the CMB. And so recall that is theta sub s, that's the angle on the sky of this acoustic oscillation feature in the cosmic microwave background. And it's basically given by the ratio of the sound horizon and recombination that I talked about at the beginning to the co-moving distance that photons traveled after recombination to get to us today. And again, I'm trying to rewrite these quantities in terms of something that gives an overall scale and something that's telling me about the just the shape of the expansion history. And in particular, because the sound horizon only depends on early universe physics, it's basically telling me something about the nature of the matter to radiation to matter transition in the early universe. And the late universe bit, that is what the co-moving distance traveled and the denominator is sensitive to, is telling me about the late universe, so the matter to dark energy domination transition. Okay, so if I rewrite these things, using those particular universes, matter radiation for the top, matter dark energy for the bottom, I can rephrase this question as follows. I have the ratio of the sound horizon, which is telling me what was the co-moving horizon size at the time of equality, of matter radiation equality. And then this integral in green, which is really just sensitive to how soon after the time that matter and the matter and radiation densities were equal did recombination occur. And then similarly in the denominator, I have inverse H naught like before, and some integral that really only cares about when the transition from matter domination to dark energy domination happened. Turns out that the bottom is given by a hypergeometric function. So if you like 2f1, here you go. And you can just, about the lambda CDM best fit, the dependence is approximately thus. Similarly, once I plug in the form for the sound speed for the photon baryon plasma, C sub s, long story short, there's also an analytic solution. And if I approximate, take an approximate power law about the lambda CDM best fit, this is what I get. Okay, like lots of details. The takeaway that I want you to get from this is that the angular size, if I can measure theta sub s, the angular size of the acoustic oscillation feature in the CMB, I learned something about what the co-moving horizon size in the early universe was. So this is like, yeah, how this is controlling the size of the sound horizon. I also need to know how long after matter radiation equality recombination happened. This turns out to be well measured by the particular shape of the CMB, as we'll see in a couple slides. And then also the size of this R, the baryon to photon ratio, just the ratio of their energy densities at the time of recombination. Okay, and so since as I will justify shortly, the green bit is well measured. The red bit, the fractional matter density is well measured by late universe distance measurements. And the radiation density, this little omega R, is also known to like 6 decimal places or something. I basically can see that if recombination happened earlier, so A sub star is smaller, then I would need to make H naught bigger to compensate and get the angular size of this feature to be the same. Okay, there's a lot of math, and let's go back to some pictures. If I do the exercise of just fixing the size of the sound horizon by adjusting H however I need to do, that basically turns out to be I need to increase H with 3 powers of the electron mass. And so if I do that, then okay, clearly the location of these peaks are in the right spot now. However, the shape of the spectrum is not quite right. The first effect, so if I just kind of look at this, it seems like broadly, if the electron is heavier, there's more power at all L. That seems to be the net effect. So that's sort of reminiscent of the so-called radiation driving effect, which is where in the early universe, you have the photon baryon plasma. It's sourced by gravity. The metric potentials, the scalar metric potentials, start to decay in the radiation era once they cross the horizon. And so this decay kind of coincides with the oscillations of the plasma and acts as like a brief driver just in this first like half oscillation. And so this acts to amplify the CMB at certain scales. And moreover, it's scale dependent because recombination happens to occur right around the time when I'm transitioning from the radiation era to the matter era. So this effect is modulated by this fact. So the way to fix it, to get the ratio of the redshift of equality to the redshift of recombination, the same is to increase the matter density in proportion to the electron mass. So what this does is now leaves me with, I basically have this like alternating modulation in the heights of these first couple peaks. And this is known as the effect of baryon loading. So the amount of baryons, so that how much the baryons contribute to the sort of weight of the plasma affects the zero, shifts the 0 points of the acoustic oscillations, and the more I shift this, the more the peak heights will be different. So basically, if I can make it so that the energy density in the baryons is large enough to counteract the fact that recombination is happening earlier, again by increasing the baryon density in proportion to the electron mass, and then I fix the total matter density. Now we can see just the radiation driving effect. So now I'm doing the sort of opposite game that I was doing in the last slide, and so now I just see this coherent but still slightly scale dependent shift in power in the CMB. Okay, to pull it all together, if that was a bit too much detail. Long story short is that if I increase the baryon density and the CDM density in proportion to the electron mass, and then I use H naught to get the angular size, the sound horizon, correct, this is what I get. I basically, nearly perfectly reproduce the CMB at, even with electron mass shifts of 20% in either direction. This is exciting. This basically means that the CMB does not really, in principle, does not know what the electron mass is.
But may I ask maybe, is there an effect on the damping tail?
Yes. Since I'm running a little short on time, I'll skip the details, but if you look at the way that the Thomson scattering cross-section scales and whatnot, you basically get that the damping scale moves in proportion to the sound horizon for free. And so that means the angular position of the damping scale is unchanged along this degeneracy direction that we're already using. That's for free. Thank you, Juva. Okay, so so I'll skip the summary and move on to talk about the other cosmological probe that I'll use in parameter inference, which is low redshift distances. So here I'm plotting the when we infer the BAO, the baryon acoustic oscillation scale from galaxy surveys, I'm plotting that quantity, so that using that feature to give me a distance measurement, to calibrate a distance measure. And I'm just plotting this relative to the lambda CDM best fit. So just being along the line one means that I'm doing just as well as lambda CDM at fitting these data points. And clearly the electron mass along this degeneracy direction that I just presented is messing with these distance, the ability for this model to reproduce these distance measurements. So why is that? Well, remember that in a flat universe, these distances are again overall scale given by H naught and the shape of the late universe expansion history. If I have a bunch of measurements at different redshifts, I'm kind of mapping out this expansion history as a function of redshift. And so the original proposal in this paper from a few years ago was to invoke curvature, as I mentioned before. This basically allows you to change the distance measurements as a function of redshift in such a way to fix things up. But remember, as I argued several slides back, to avoid a large thermal mass, you necessarily have a scalar field with a non-negligible contribution to the total matter density. Moreover, since increasing H, since achieving a larger H naught required me to have a larger energy density in dark energy, I basically along this degeneracy direction, basically misbalanced the amount of matter to the amount of dark energy, and that's what determines the shape of the low redshift universe's expansion history. But as I said before, the scalar field becomes matter-like when it starts oscillating. So I basically have a built-in way, not like a knob, like it has to be the case, that I have something that is adding back some matter in the late universe to offset the fact that that I've overcompensated by I have too much dark energy compared to what I should have. So just to give a bit of a more concrete picture, this is the sort of the standard redshift evolution of the various constituents of the universe. The red is the radiation, which starts to become unimportant around the time of recombination. The orange is the regular CDM and the baryon density. And then the green is dark energy, which only becomes important at late times. And I now have this additional component, the scalar field, which quickly becomes important soon after recombination, and then just redshifts like matter. And so it basically just means that the matter density that I have in the late universe is slightly bigger than the matter density that I have in the early universe. And so taking this in mind allows me to, for positive increases in the electron mass, fix up the low redshift distances and basically totally reproduce what lambda CDM would give me. The reason why I can't add negative energy density via the scalar field, so I have no way to fix up the electron mass when I'm postulating that it's lighter in the early universe rather than heavier. But of course, if we want to increase H naught, then we are only really talking about heavier electrons. Okay, any questions here before I go through the results?
I have a question, but maybe it's better to pull it in. So I'll ask the question and you decide what you want to do. So how do you incorporate, right? So there's some amplitude of inhomogeneity at recombination. And so you're just seeing that's just built into like constraints from the CMB power spectrum?
Yes. Are you asking about the fluctuations in the scalar field?
Yeah.
Yeah. So yeah, I've sort of, I'm secretly going to assume that there's no so-called isocurvature perturbations, or at least they're negligible in this field. So this is, when you have a light field, an additional light field during inflation, you expect this light field to have some amplitude of fluctuations. But this is proportional to the energy scale of inflation, and that's, unfortunately still a free parameter for us. So we're free to assume that the scalar field only inherits the adiabatic perturbations that the rest of the constituents have. That makes sense. And since those are 1 in 10⁻⁵ or so, and they also redshift, with time, the spatial modulation of the electron mass is not important.
And so in principle, observationally, how would you constrain it?
Like if it existed? Yeah.
This would be a second law. Okay.
It would be small, but I mean, people have, so these quasar absorption measurements do sort of map out the sky a little bit, and people have done searches for spatially varying constants. And if I'm remembering correctly, I think there actually is some like 2 sigma detection of spatially, but like, I wouldn't take this too seriously. We're talking about like a dozen measurements and stuff. But yeah, you could do things like this and if it were large, then it would also change the way the CMB responds. Okay, cool. So I don't have a ton of time, so I'm just going to quickly say, long story short, we had to implement a new treatment of scalar fields in the standard cosmology code class for the purposes of this project. It's effectively just because the Klein-Gordon equation is highly oscillatory, and so it's really intractable to do parameter inference for tens or hundreds of thousands of parameter points if I've got this field that's oscillating thousands of times in each of these. So there's a new well-motivated, sort of semi-analytically grounded approximation scheme introduced by Weiner and Sam Slaglia just last year, and matches onto some effective fluid description that allows you to skip the computationally expensive part of the scheme. I'm mostly just saying this in case it's of interest to people in the room who have worked on similar things before. But yeah, so with that said, let's take our model and let's run parameter inference using just CMB data, so just Planck measurements. Here's what we get. Well, I see a degeneracy direction, and it seems to be everything increasing with the electron mass. I'll point to things in a second. Just as I'd hoped. Of course, by my arguments, you would have expected that any electron mass would be allowed, and so any H naught would be allowed. But if you look carefully, this red point is the lambda CDM best fit. And so what the CMB seems to prefer in this model, where I can have early or late recombination, the CMB seems to tell me that recombination should have happened much later than it does in standard cosmology. This is a bit weird. At least the sort of the physical arguments that I gave for how the parameter space should behave have borne out, but I had the expectation that these lines, these narrow posteriors, sort of extended arbitrarily, up and down. Just to just focus a bit more on the. And I'll just say that this result is effectively the same thing. You get the same thing for vanilla early recombination without a scalar field, this result is consistent with what previous work found, but no one really talked about it. So I'll talk about it for a second. Okay, so just looking in more detail, this is the same result. Electron mass increasing. So this is the fractional change from early universe to today. As it increases, I infer a larger H naught. H is just H naught in the units of 100 kilometers per second per megaparsec. And I have some upper, I just have some upper bound on this C thing, which I'm using to denote what fraction of the CDM density is contributed by the scalar field. So that's too bad. I mean, this isn't really surprising given that I only argued that this energy density would be helpful if I had earlier recombination. And so since it seems like the CMB only wants to have later recombination, what this is telling me is that there's no need for this scalar field to contribute meaningfully. So this is already, I mean, if you're hunting, H naught of 74 or whatever, then this is disappointing. But it's also, a bit of a puzzle because, there has to be some effect going on to drive this. Before I get into that, I'll just warn that because these posteriors are so broad, there's actually a strong sensitivity to priors. And it turns out that standard choices made in most analyses of cosmology are implicitly using a prior that amounts to a 1/h prior. I don't know if people noticed this before, but that certainly has some impact when you have posteriors that are as broad as like, I don't know, 30% or something. Of course, if you believe me when I say, if you look at this plot and compare it to this plot, if you compare the prior to the posterior, there is still some input coming from the CMB. So I'm not just showing you some funny business from the prior. Okay, so to see why this is happening, well, I was being a bit misleading before by showing you the CMB on a linear scale. So now I'm going to show you on a log scale. This is the same plot as before. You can see that there is an effect at low L. So the CMB is not totally degenerate in this model. In particular, if I zoom in on these first like 30 multiples or whatever, and I overlay the Planck data, first off, forget about the comparing the colored curves. If you indulge me in some chi by eye, you can see that a lot of these gray points, the means for the Planck data kind of skew low. And so even though this is large angular scales, so cosmic variance limits how much information I really have, this is still a trend. And so it still will have an effect when nothing else in the CMB is providing meaningful constraints. This is the only thing I have. And so that's that's what's going to reflect in my parameter inference in the posteriors. So of course they are broad, so there's not a lot of information, but you can also kind of see just by eye that the data seem to want to drag these curves down. Yeah.
Can I pick this the rounding with respect to index somehow? Is it possible?
That very well could be. It's not something I've tested, but certainly, yeah, having a more detailed initial power spectrum could do that. But for what I have done, so let's talk about these colored curves. Remember that as I increase the electron mass, I'm along this degeneracy direction, I'm increasing Hubble. And that means I'm increasing the amount of dark energy. And so what's really going on here is that I'm increasing the amplitude of the so-called integrated Sachs-Wolf effect, the ISW effect, which is what happens when the universe transitions from matter to dark energy domination. Gravitational potentials go from being constant to decaying. And this decaying, if you imagine a photon traversing a potential that is becoming shallower with time, effectively amounts to a blue shift. And so that will boost the amplitude of power on these extremely large scales, because this is something that's happening at very late times. And so if I take this seriously, it looks like the CMB is telling this model to make a recombination as late as possible so that I don't have to have any dark energy. So I have no ISW effect. So if you'll indulge me, we would interpret this as saying that the CMB doesn't favor dark energy, it favors late recombination. Obviously, this is not our only probe of cosmology, so I'm not asking you to take that claim seriously. This is just the interpretation for this one particular parameter inference with the data that I've chosen. Okay, so for time, I'm going to skip ahead. When I throw in VAO distances, this basically snaps me right back on a mass shift near zero, electron mass shift near zero. Fortunately, we can see that adding in this low redshift distance information does, roughly correlate the, the amount of the contribution of the scalar field to the size of the mass shift, and this is what we expected. So at least there's that. But at the end of the day, what this model means for our inference of values of H naught is not much. The posterior broadens quite a bit. I think the 1 sigma error bars triple. But this is kind of typical for models that try to adjust the Hubble tension. They don't really move the median that much, but they do broaden the error bars. And so not really what one would want from a true solution. And the one other thing that you can see in this little figure is just that the model does perform slightly better than just vanilla early recombination. Again, precisely because we have this way to fix up low redshift distances that the vanilla scenario without a scalar field does not have. Okay, I have just a couple minutes, so I'll just highlight some additional phenomenology. So scalar fields have a free streaming scale. They do not cluster below some scale associated with its mass. And so this free streaming subcomponent of dark matter will suppress the growth of structure. And you can see in the, this is again the same results that I showed previously. So red is lambda CDM, gray is the vanilla early recombination, and then blue is our scalar field models. And along this direction is an effect due to allowing the matter density to be different than it is in lambda CDM. That acts to both increase H and sigma 8, our usual measure of the amplitude of matter fluctuations. But when I have a scalar field, I actually get this orthogonal direction, which is what we would want, given that our weak lensing probes tell us that sigma 8 maybe should be smaller, and that the Cepheids are telling us that H should maybe be bigger. And this is because the scalar field can marginally suppress the amplitude of structure. There's also atomic clocks that kind of operate similarly to the quasar absorption, but if you can get a time series of, so atomic clocks are incredibly stable and precise, and it gives us a way to search for time-dependent shifts in the electron mass that might be due to this model. There's additional phenomenology for these EP violation experiments, in particular for these models. The degree of violation of the universality of free fall will depend on altitude, and so there's other things that you can imagine doing, but it's exactly noon, so I'll just put my summary slide up and conclude. So thanks.
Thank you, Zach. Any questions? Well, actually, I have one question. So if you can go back to the constraint plot with Planck only results, with long degeneracy direction. Yeah, here. So if I were to impose the shoes H naught prior here, like what kind of value of delta M would I see?
Yeah, I mean, right, so first, just to put that question in perspective, if I really had gotten that perfect degeneracy, like for arbitrary values of electron mass, then I would have been able to say, okay, so basically cosmology allows anything to happen. Now I'm free to impose this prior from shoes and just pick out the value of H that I want, because this is the only way that this model knows what H naught is. So if this, if this posterior and H naught were completely flat, that would be the case. So you can sort of see the right end of this plot is like at 75. So roughly where there's a bit higher than where the shoes prior is centered. And so since this posterior is extremely broad, it would certainly snap on. It would just be brokering a compromise between these two different preferences. One for one very weak one for very small h and one relatively strong one for large h. But since that's two measurements that are discrepant, it's I would interpret any sort of parameter inference using both with a grain of salt.
But just very naively, I would detect some fluctuation of the electron mass, but
Indeed.
probably no rho phi, right? Seems to me.
Well,
Planck only plus shows.
yeah, it's hard to see on here, but I suspect that if you're really injecting a strong preference for an increased electron mass, given this degeneracy, the posterior would look fairly different than what we see here.
Mm-hmm.
Yeah.
Thank you. More questions? If not, let's thank Zach again.